Hi, in this video, we're going to take a look at two topics, calorimetry and latent heat. Although calorimetry is a relatively short concept, a calorimeter is really just a thermos, and it's used for measuring things like heat capacity. So that's why it tends to make it into textbooks. As a problem-solving device, it actually makes some fairly challenging situations, and I don't know if it really contributes to learning that much, but I'll just describe what the process is. A calorimeter provides an insulated or thermos-like environment where we can add we can put cold stuff in the calorimeter and add hot stuff to it and see what the resulting temperature looks like. There is actually an example of calorimetry that's going to show up in one of our quizzes coming up, a scenario quiz. So I will show a quick video about how to deal with a calorimeter problem. Essentially, it's the way that Native Americans used to enrich maple syrup. So I'll do an example like that. But it does tend to be a little bit challenging, because what happens is that the hot stuff will give off heat to the cold stuff until they come to the same temperature. And then when both materials are at the same temperature, then heat no longer flows. So I'll include a lesson about how to deal with calorimetry. But I really wanted to spend some time on latent heat, because this is an interesting concept that sometimes is counterintuitive. Latent heat means hidden or not obvious heat. There's a very famous graph that shows up in all sorts of textbooks, and it features on the vertical axis the temperature of a sample of water changing as heat is being added. But there are definitely some places here and here where the temperature doesn't change as heat's being added. And the reason for that is because we're going through a phase change. This is melting, and this is vaporization. The melting process requires energy because we're dissociating bonds. So we add heat, and the very strong bonds between molecules that are in a solid form are being loosened up into water, which still has pretty strong intermolecular bonds, but less organized. As you know, ice is a crystal, and water is a liquid. Then as we continue to add heat, the liquid water is going to increase. But the most important thing to notice is that the temperature of the sample can't increase until all the ice has become water. And then the temperature starts to increase. And when we hit vaporization, and that sharp point right there is usually some kind of smooth curve in practice. But then we're undergoing a phase change. And the temperature cannot increase until all the water has become steam, and then that sample of steam can then increase its temperature. So the bottom line is that this pink zone right here is a tremendous amount of energy. So when we hear meteorologists talking about, oh, this is a very energetic storm, this is where the energy is coming from. It's phase change between water and water vapor. So here's some examples of latent heat, and we can just sort of scan things really quickly. Heat of fusion, so this is a phase change between solids to liquids and liquids to solids, and vaporization, liquids to vapor and vapor to liquids. But one important thing I want to point out when we do some problem solving around this is that the units are very different. Look, it's kilojoules per kilogram. We got to be on the watch for this, because in our previous table that had heat capacities, it was joules per kilogram. Okay, so we're going to make a big deal about that when we go to do problem solving lessons. So just once again, why vaporization is a cooling process, or condensation is a warming process, or why there is, some kind of process. We all know that, human beings sweat, and this is a way to regulate our temperature when we exercise or we're under stress. So it gives off heat. Well, actually, we're one of the few animals that do sweat, and so other animals have a real hard time regulating their temperature, especially when they're doing really strenuous stuff. So let's consider, why is vaporization a cooling process? So I have kind of a silly little cartoon here to walk through. Let's imagine that we have a bunch of molecules and they all have little personalities, and we have a bunch of molecules that are in a liquid state, and then some H2O molecules that are in a vapor state up here. And of course, if we, put some human emotion to these things, maybe these molecules are a little jealous because of their brethren that can kind of fly about without being tied down by all these intermolecular forces. So anyway, this one really wants out of there, says, hey, can you hit me and give me some energy? I need to be free. Okay, great. So in an energy sharing collision, this molecule got enough kinetic energy to break its bonds and be free. But as it leaves, it takes away a higher kinetic energy than the average. And that energy is no longer available for energy sharing collisions. So the average temperature is going to decrease, because temperature is proportional to the average kinetic energy. So when a large chunk of energy leaves, the average kinetic energy goes down. I'll let you read the punchline.